Hello, everyone. Thanks for watching my presentation. My name is Hojatian. I'm a PhD student at Polytechnic Montreal under supervision of Professor Leduc and Professor Firgun. My research project is applied machine learning in telecommunication system, especially massive MIMO and 5G. Today, I will give you a summary of my research topic, and I will present briefly our last submitted paper. At first, I explain a bit about the context and my research topic. Then, since we use deep learning in our method, I describe the dataset generation and offline procedures. I will show you how we deployed unsupervised learning to design hybrid beamforming, following by simulation results and conclusion. Let's start with the system description. You may hear about 5G recently, especially in recent event held by Apple to introduce the last version of iPhone. 5G communication was one of the main features in new release iPhone. But what is 5G? 5G, fifth generation of wireless communication, is the new release standard by 3GPP, cellular network standard, and it allows a high degree of heterogeneity in terms of service. 5G wireless technology is meant to deliver high peak data rate, more than 10 gigabit per second, ultra low latency, less than 1 millisecond, more reliability, and massive network capacity or massive machine type communication. To achieve these goals, the breakthrough technologies are needed in 5G. One of these crucial technology which has been introduced in 2010 is massive MIMO. Before I talk about massive MIMO, let's describe MIMO system. MIMO, multiple input, multiple output, is a method for multiplying the capacity of radio link using multiple transmission and receiving antennas. In MIMO, it's tend to use 2 or 4 antennas, while in massive MIMO, this number increased to basically more than 100 antennas. In massive MIMO, despite of all of its hardware challenges, it provides many significant opportunities. That one of these is excellent beamforming. What is beamforming? Beamforming is a technique that focuses a wireless signal toward a specific receiving device rather than having a signal spread in all direction from a broadcast antenna. Therefore, a precoder is needed in transmission to informing the signal beam. The fully digital precoder or beamformer can be used for beamforming. However, as you can see, it's required one RF chain for each antenna, and RF chain is a radio frequency chain. And since in massive MIMO it's assumed to be more than 100 antennas, a large number of RF chain is required. To address this challenge, which leads the system to be costly and energy efficient, hybrid beamforming is introduced, where the combination of analog and digital precoder is used for beamforming. The analog precoder derive the beam, and digital precoder do the baseband signal processing. As a result, the number of RF chain is reduced, while the performance of the system maintained. Now I want to explain what is codebook. The analog precoder is phase shifter to drive the beam and reduce the design complexity. Analog precoder defined to perform a limited quantized number of states. We define each state as code word, and all of these code words together known as codebook. Many solutions to design the hybrid beamforming has been proposed since 2013. However, it has always been a complicated task due to hybrid structure of the precoder and also imperfection of the RF chain. Hybrid beamforming design requires channel state information, CSI, at the base station because the beamforming should be done for each user based on its channel. And finding the optimal solution for hybrid design is computationally heavy, especially in real-life network. So we propose a RSSI-based receive signal strength indicator, hybrid beamforming with deep learning. It's owing to the fact that the deep neural network help us to reduce the amount of feedback we need from the user and no need to have full knowledge of CSI. Now let's see how we generate the data set and what's going on in the offline mode. To generate the channel vectors, we use deep MIMO dataset. It is a millimeter wave massive MIMO dataset. We generate channel matrices by applying ray tracing method. We consider three scenarios. First one, we consider the limited area. Second, the extended area. It is larger than the limited area and cover more user position. And finally, the crossroad. It is located at the intersection of the street. Let's take a look in the entire process proposed solution. First, in offline mode, we designed the synchronization signal. The synchronization signal is used for initial access to achieve the RSSI, and they will design in such a way to have a maximum information about user's channel. Then we designed the codebook for analog precoder to reduce the design complexity while providing maximum performance, as I mentioned before. Next, we trained the deep neural network to design the hybrid beamforming in the multitasking network. So the input is RSSI and the output are the precoders, analog and digital. Finally, in online mode, the initial access begin to achieve the RSSI. Then the DNN is in the testing mode provide the precoder, and the data are transmitted in the downlink channel by hybrid beamforming design. Now it is time to talk about the unsupervised hybrid beamforming. Why unsupervised learning and why it is so important to design the hybrid beamforming? Supervised learning methods proposed for hybrid beamforming design require optimum solution for hybrid beamforming vectors as target in such a way that the deep neural network try to minimize the distance to those vectors using MSE as loss function. In cellular network, each base station has individual characterization based on its environment and it's unique. Therefore, in supervised learning, a data set for each base station must be provided separately, consist of the optimal solution as target. Therefore, it needs a huge amount of time and cost to train the deep neural network in all of these base stations. On the other hand, in the unsupervised learning, the data set preparation and deep neural network training would be much more easier than supervised learning. As you can see here in the chart, in the training phase, we got the support of the CSI to train the deep neural network, and in online phase, we only use the measured RSSI from the base station. So it's shown that using unsupervised learning is crucial and save a lot of energy and cost in hybrid beamforming design. We proposed two approaches to design the hybrid beamforming. The first one called the HBF-net. The DNN is trained to design the hybrid beamforming in regression task and select the analog precoder from our proposed codebook in classification task. It is less complex than our other proposed approach. However, misalignment between digital and analog precoder reduced the sum rate performance. Our metric to evaluate the performance is sum rate or throughput, bit per second per hertz. It is the sum rate of all users. In other approach, AFP-net, the deep neural network is trained to design the fully digital precoder and select the analog precoder from the codebook. Then digital precoder of the hybrid beamforming can be found using the inverse of these two outputs. It's more complex than HBF-net because it's using the inverse. However, due to alignment between digital and analog precoder, it has better sum rate performance. And it is the multitasking network we propose for hybrid beamforming, since we use real value networks, weights and biases. And the digital precoder is a complex value. We separate the output of the deep neural network in regression part to real and imaginary part, and then using complex value computation, find the sum rate performance. For classification part, in both approach, DNN deep neural network is trained to find the best codebook among all available codewords in the codebook in the classification task. Let's look at the proposed loss function. As you may remember, since we use unsupervised learning, we defined a new loss function based on sum rate, where we try to minimize the negative sum rate. In other words, we try to maximize the sum rate using multitasking deep neural network. In HFPNet, HBFNet, digital and analog are jointly designed. In AFPNet, fully digital precoder designed and using pseudo inverse, find the digital precoder. Here again, we defined to directly maximize the sum rate. Now let's evaluate our methods. We use a deep MIMO channel model, and here is sum rate performance for extended area. We compare the DNN method to 3 other methods, where we propose one of them, which is HSHO, and the 2 other methods, OMP, orthogonal matching pursuit, and PZF, phase zero forcing, is well-known solution, not deep learning solution. It can be clearly seen that our proposed method outperform 2 other conventional methods in extended area, crossroad area, and delimited area. So in all 3 scenarios, our proposed method outperform other solutions. Here also we showed that the sum rate performance is stable by increasing the number of users, number of antennas, and number of users. And you can see that our HBFNet and AFPNet both are stable by increasing the number of antenna and number of users. To sum up, we propose RSSI-based hybrid beamforming. Using DNN deep neural network help us to reduce the amount of feedback we need and improve spectral efficiency. We propose unsupervised learning, and it is shown that the deep neural network can be trained only by channel measurement without knowing the optimal solution. Also, in dataset generation, we propose synchronization signal design for initial access, codebook design for analog precoder, and non-deep learning method to design the hybrid beamforming as a baseline to evaluate our deep neural network performance. For additional information about my presentation, please check out our last paper in arXiv, which is submitted on Journal of Transaction and Wireless Communication. Thank you so much for your attention.